Hello everyone, this is Rajkumar Singh. I welcome you all in my lecture series on quantum physics. You have been listening to my lectures on quantum physics. Today we will discuss on Zeeman effect as an application of perturbation theory, one of the method of approximation method in quantum mechanics. Zeeman effect is the splitting of spectral lines by an external uniform magnetic field. And it is a direct confirmation of space quantization. When we consider the electron spin, then it is the case of anomalous Zeeman effect. But when we do not consider the electron spin in the calculations and the electronic transitions, this is the case of normal Zeeman effect. So in this lecture, we will be talking about Zeeman effect, that is the normal Zeeman effect. Now what happens in normal Zeeman effect? When we observe a singlet spectral line, that is a spectral line due to transition from some higher energy level to the lower energy level, in absence of any magnetic field, this is a singlet spectral line. But when the same situation is viewed in presence of magnetic field, normal to the magnetic field, we see that that singlet spectral line is splitted into three plane polarized components. There is one central unshifted line with electric vector vibrating parallel to the magnetic field direction. This is called the pi component, and there are two other lines which are equally shifted on either side of central line with electric vector perpendicular to the direction of magnetic field. This is called sigma component. As you can see in this picture, we have this singlet line of frequency nu naught, known as the pi component, in absence of any magnetic field. But when the same spectral line is seen in presence of uniform external magnetic field, besides this central line nu naught, on either side of it we have two extra lines, one with frequency nu naught minus del nu and the other one with frequency nu naught plus del nu. That means these two lines are shifted on frequency scale by the same frequency difference on both sides of it, and these are the sigma component. Now let us consider a particle of mass mu and charge q in a central potential Vr subjected to an external uniform magnetic field B. The unperturbed Hamiltonian of the system will be, as usual, H naught equal to P square by 2 mu plus Vr. Now since we are discussing the normal Zeeman effect, so we have to ignore the spin of electron. So we will only concentrate on the orbital motion of electron around the nucleus. So in this case, the interaction of magnetic moment with the applied weak magnetic field produces a perturbation Hamiltonian term given by Hp equal to mu b by h cross b dot L, where L is the orbital angular momentum and mu b the Bohr magneton. Now the eigenvalue equation for hydrogen atom we will consider Q equal to minus E, and let the applied magnetic field be along z direction. Then Hamiltonian of the hydrogen atom system in presence of uniform external magnetic field will be given by H equal to H naught plus Hp. So for H naught we have P square by 2 mu minus E square by R, as we have taken minus E for charge on the electron in place of Q, plus the perturbation Hamiltonian mu b into b by h cross into Lz. Now since h naught commutes with Lz, the z component of orbital angular momentum operator, the operator h, h naught and Lz mutually commute and hence possess a set of common eigenfunction which in the spherical coordinate can be expressed as psi nlm function of r theta phi. This is equal to rnl function of r and ylm function of theta phi, where rnlr is the radial wave function and y lm theta phi is the spherical wave function, and the subscripts n, l, m are the good quantum numbers, n the principal quantum number, l the orbital magnetic angular momentum, and m the orbital magnetic moment. So the eigenvalue equation as written as equation 3 in the eigenstate ket nlm, it will be given by Bray nlm h nlm. This is equal to nlm h naught plus mu b b by h cross lz. This we have taken in place of the h operator h, and then the ket nlm. Now on the right side we separate these as the two different terms. So first term is Bray nlm h naught ket nlm, then plus second term is Bray nlm mu b b by h cross lz nlm ket. Now this expression is considered as the value En naught, which is the unperturbed energy without any presence of external perturbation, and for the second term we have mu b b by h cross being the scalar quantity. We take it outside of this expression, and we are left with Enlm. We are writing for the expectation value of this, and that is equal to En naught plus mu b b by h cross ml h cross, where this ml is the orbital magnetic moment, and it takes on values from minus L to plus L through 0. That means it has 2L plus 1 values. And En naught is the unperturbed state energy and is equal to En naught equals to minus mu e to the power 4 by 2 h cross square n square. Therefore Enlm, the energy in the state nlm, that is equal to En naught, the unperturbed state energy, plus the energy contribution coming from the perturbation, that is mu b b by h cross ml h cross. So this h cross cancel out with this h cross, and we are left with Enlm equal to En naught plus mu b b into ml. Or this can also be written as Enlm equal to En naught plus ml omega l h cross, where omega l is known as the Larmor frequency. Thus, when a hydrogen atom is placed in a uniform external magnetic field and the spin of electron is ignored, then atom's spherical symmetry is broken in the ground state. Each ground state energy level with angular momentum L is split into 2L plus 1 equally spaced levels with spacing delta E equals to mu b into b, or that is also equal to omega L h cross. This equidistant splitting of energy levels is known as normal Zeeman effect. Now let us understand this. From this equation we have Enlm equal to En naught plus mu b into b into ml, h cross cancelled out with this denominator h cross. So this ml takes on different values from minus L to plus L. If we take L equal to 1, then this ml will have three values: minus 1, 0 and plus 1. Accordingly, the expression for Enlm will be 3. One of the expression will be En naught plus 0. If we take ml equal to 0, so this becomes 0. So that is the unperturbed state energy. And when we take ml equal to minus 1, then we have expression Enlm equal to En naught minus mu b into b. And when we take ml equal to plus 1, then we have Enlm equal to En naught plus mu b into b. So thus, for a given value of L, since ml has 2L plus 1 values, so we have different energy expressions for Enlm, and that was being discussed in our next slide here that the spin of electron, when it is ignored, then the splitting which is equal, this is called normal Zeeman effect. An important observation here is that when we exclude the spin of electron in the calculation, we find that atoms' spherical symmetry is broken, and each ground state energy level with a given angular momentum L splits into 2L plus 1. Now, these splittings are guided by certain selection rules. What are those rules? Delta M equal to 0 and plus minus 1. That means for a given transition, the ML value will change strictly with this one, delta M equal to 0 and equal to plus minus 1. Whereas transition from M dash equal to 0 to M dash equal to 0 is forbidden. It is not an allowed transition. Now, there is a contradiction, what we see in the normal Zeeman effect and what we observe in the experiments. That in normal Zeeman effect, each energy level splits into an odd number of 2L plus 1 equally spaced levels. This is totally in disagreement with the experimental observation. Now, what is the experimental observation? Experimental observation says that there are even number of levels, and that too the energy difference between the levels or the energy spacing is also not equal. So this suggests that the angular momentum is not an integer but half integer, because for half integer values of L, this 2L plus 1 will become even. So this calls for inclusion of electron spin in the theory, and we replace angular momentum L by total angular momentum J, which is defined as J is equal to L plus S in the vector form. This leads to splitting of each level into an even number of 2J plus 1 unequally spaced levels, known as anomalous Zeeman effect, which is the topic of our next lecture in this series. Now let us understand these transitions. We have three states for L equal to 0, L equal to 1 and L equal to 2. For L equal to 0, the number of splits 2L plus 1, this is equal to 1. 2 into 0, that is 0, plus 1 equal to 1. And similarly for L equal to 1 we have 3, and L equal to 2 we have 5. So these are the 5 corresponding to ML values minus 2, minus 1, 0, 1, 2, and similarly these are the 3 levels corresponding to ML values minus 1, 0 and 1. So we have the singlet transition here from L equal to 2 and to L equal to 1 in absence of any external magnetic field, and this is that singlet line. And these are the different possible transitions conforming to the selection rule: delta M equal to plus 1, delta M equal to 0 and delta M equal to minus 1 in presence of external magnetic fields, and we have these two shifted lines on either side of it, and this is the different spectral lines. So with this we conclude our discussion on Zeeman effect. In our next lecture we'll talk about anomalous Zeeman effect. So with this I express my thanks to you for your kind patience. Thank you so much.